is graphs of equations, and we're just going to stick to 2 dimensions as far as this class goes. So you got your, your x and y values, and so the first thing we're going to talk about is graph of equations by plotting points. How are we going to graph some equation that's given to us? Notice we're not talking about functions yet. If you're familiar with functions, that's going to be later on that we're going to start talking about functions. Chapter 3, if I recall correctly. Then we're going to talk about finding the intercepts from a graph, and then find the intercepts from an equation. So we're going to introduce what intercepts are, how to find them when you're looking at a graph, how to find them when you're just looking at the equation, you don't have the graph. And then we're going to start talking about testing an equation for symmetry with respect to the x-axis, y-axis, and origin. And you may not even know what the origin is, but we'll talk about that. So that last one, that's kind of the more difficult part, I would say, of this section. Testing for symmetry from a graph is not tough, but doing it from an equation is a little bit more difficult. All right. So, first things first, let's talk about what this is. Anybody knows what we call this picture here? There's a few names for it. The simple one, which you may have heard, is the XY plane. It's a flat surface that has X's and Y values, so the XY plane. The other one is the Cartesian plane, which you may have heard of, the Cartesian coordinate system. That comes from that as well. We'll use, both when we were referring to it. Mostly we'll just call it a graph when we really are talking about it, because that's just the simplest way. But those are some different names for that. There's different parts of it. You got your bold lines. Does anybody know what this line right here, the horizontal line? That's the x-axis. That is the x-axis. That is the axis in which the x values increase and decrease. As you go to the right, they increase. As you go to the left, they decrease. And they continue going. That's why they have the little arrowheads. What about this vertical one? The y-axis. Yep, good. That's where the y values increase upwards, they decrease downwards. So your y values are increasing this way, decreasing this way. If you go in this direction, the y values and the x values are increasing. Go this way, the y values and the x values are both decreasing. And you can do it the other direction too. I mean, y is decreasing, x is increasing in this way. And if you go this direction, y is increasing and x is decreasing. So, the other thing is where the 2 axes meet. What is that called? That is the origin. And that is the point 0, 0. Okay. And you can think of it kind of like a, the way that I think about it, maybe it'll help you, is that, when the universe started, there was the Big Bang, right? And everything came out of one point, and it just spreads out in all directions. Well, that's kind of like this. The graph starts at the origin and just spreads out in all directions. We only have really 4 directions to go because we're talking about 2 dimensions here. And one last thing that we talk about is the 2 axes basically cut the Cartesian plane or the XY plane into 4 distinct pieces. Anybody knows what we call this one? That's the quadrants, and it's quadrant 1. Quadrant 1. They use Roman numerals for it. And so the shorthand, I'll write in blue so it sticks out. It's just Q1. And this always confuses me because they don't increase in the way that I would think they would go. It goes next to this one, which is Q2, and next to this one, which is Q3, and next, finally, to this quadrant here, which is Q4. I mean, in algebra, we can use the different quadrants to talk about things, but honestly, if you've taken trades before, then they're a lot more useful than that. A lot more important. Because depending on what quadrant you're in, things are negative and positive. Something you have to use. Any questions on that? Oh, okay, no worries. All right, so an ordered pair consists of an x and y value written as x comma y. So when you have an ordered pair, and I'll write it here again, it's always going to be x comma y. And that allows us to find a specific point on our xy plane, on our Cartesian plane. If we added another dimension to it, we would need 3 values, right? Then another, we'd have 4, 5, 6, 7, how many dimensions we want. But since we're only dealing with 2, we just need 2 values. And since it's only 2 values, we call it an ordered pair. They're in order from x comma y. And so if we're trying to find where the point 4 comma 3 is, that's going to be where x is equal to 4 and y is equal to 3. Gets kind of confusing because it looks similar to the interval notation that we used earlier. So in some mathematics, you have to say, okay, well, we're talking about ordered pair here rather than an interval. Usually the context clues will get you there, but it is something to think about. And so if we want to plot that point, we go where x is 4. 1, 2, 3, 4. This is where x is 4. Let me mark it with like a little yellow. 1, 2, 3. That's where x is 4. We go to where y is 3. 1, 2, 3. And then you just go see where those 2 values would meet up, which is going to be that point right there. And so this would be the point 4 comma 3. That's all you got to do. Always makes me think of battleships, but they don't have net letters and numbers. You know. Any questions on that? All right, what's next? All right, so how do we determine if a point is on the graph of an equation? Okay, we don't even know how to graph an equation, but we can still work it out. So let's say you have this equation. It's 2x minus y is equal to 6. I'll write it out again. 2x minus y is equal to 6. It's a little small. How do we determine if the point 2 comma 3 is going to be on the graph of that function? Plug it in. What do you mean by that? X is a 2 is the x value, y is the 3 value. We could substitute or plug these in to the equation they give us. And so if we do 2 times 2 minus, what was it, 3? Yep. 3. And what are we going to do from there? What do you think? What do you mean by solve it?
2 times 2 and 1 minus 3.
So you're going to evaluate it, and so then we do 2 times 2 is 4, minus 3, that's going to be what, 1? Is the result we get true? Does 1 equal 6? No. So if that's not true, what does that tell you?
You don't-
It's not on the graph. Oh, sorry about that. I hit the sticky button. Any questions on that one? Oh, actually, let's do that one next. What if we have the point? They're doing the same equation. 2x minus y is equal to 6. But they give us a different point. They give us the point 2 comma negative 2. So we're going to do the same thing. We got an x value of 2. Got a y value of negative 2. Let's plug those in. So we'll have 2 times 2 minus negative 2 equal to 6. And so 2 times 2 is 4, minus the negative 2 would be plus 2. And so we end up with 6 is equal to 6, which that is true. So we call it tautology. So it's always true. And so that tells us that the point 2 comma negative 2 is on the graph. Of that equation. 2x minus y is equal to 6. Any questions on that? No, we're good. All right, so excuse me. Let's say we're dealing with that same equation. 2x minus y is equal to 6. Is there some way that we could find another point that's on that graph of that equation? We know 2 comma negative 2 is, but what if we wanted to find like another point? What could we do?
Plug in the numbers.
How will we know the two numbers?
Like basically get x point off the graph with the y point and plug it in and see if it works.
Okay, so you're saying like you could say, well, x is 3 and y is negative 3 because 2 and negative 2 worked, and we could try it out. You could do that. What's the chances of it being right though, when you do that? There's a lot of numbers to choose from, right? So can we think of a better like way to try some different values? You're on the right track, and that would work. It just it would take us forever. But what would another way that we could do it?
Would you solve for x and y?
We could. What are you thinking of doing after that? No, you don't know? Okay, so one thing that we can do is say, well, for this one, are there any limits to what x and y can be? And do y'all know what I mean by that? Remember that there's domain restrictions sometimes, right? So we have some equations or some expressions even where x couldn't be certain values or whatever variable couldn't be any values or certain values. But if we look at this one, the x and the y, they're both in the numerator, they're not in the denominator, so it doesn't matter if the denominator is going to be 0, that's not going to happen. They're not under even root, so we have no restrictions there. So both of those variables can be whatever they want. Okay? Everybody with me there? So what if I say, well, let's just make, I'm going to say, well, let's make x equal to 1. Could we find the y value that goes with the 1? How could we do that? We could plug in the x. So if we take our equation and we plug in that x value, can we now solve for y? Yeah, well, we do 2 times 1 is 2, minus y is equal to 6. So let's subtract 2. We get negative y is equal to 4. And let's divide by negative 1 to get y isolated. So y is equal to negative 4. And so when x is equal to 1, for that equation, y is equal to negative 4. So that means that the point 1 comma negative 4 is on the graph of that equation. And we could do it like, I mean, we could choose another number. We did 2 already, but we could choose 0, we could choose 3. We could choose whatever number we want for x or y, and then find out the other value. Okay. And when we get to functions, usually x will be your input, y will be output. But since we're just talking about equations right now, there's really no rules for that. You can give me one, I'll find the other one. And if you solve for one of the variables like you're talking about, you'd make it easier, right? You plug in the other one, and it would just evaluate the other one. So that is one method to do it that way. Any questions on that? So we can use that to figure out what the graph of an equation looks like. Now this is kind of a drawing graphs by hand is kind of a dying thing, because I mean you can just go to a decimals graphing thing, and that's what I use. But there's probably a billion other ones on the maybe there's a lot of them on the internet that you can use to graph things. Even your graphing calculator, if you have a graphing calculator. Probably your phone. You could probably, I know you could get graphic calculator apps on your phone. So there's a lot of different things you can do to do this, but it's a good skill to understand what those graphs look like and what they operate like and how are these points found. So that's why I want to still do it. So let me shrink this chart that I made gigantic. Okay. There we go. All right, so let's say we have this function, not a function, sorry, an equation. Y is equal to 2x plus 5. And we want to try to graph that. Now, there are skills we'll learn about this one in 2.3, actually, where we could graph it easily. But we don't know that. Well, assuming we don't know that. So what do you think we could do? Well, the chart kind of gives you a little clue into that. And what we did in the last problem we just did kind of gives you a clue into that. But we could choose some x values, figure out what their y values are that correlate to them, and then that'll give us a point. And if we get enough points, then we should be able to draw the graph, right? And so one of the rules, kind of to help you when drawing a graph, and we're not going to follow it this time, but just if you see one in a while, is whatever the highest degree is say that again. Whatever the highest degree on the variable, either variable is, that's how many points you want, plus 1 at least. So this one, the highest degree is just x to the first power. So I want at least 2 points. Not saying that 2 points is enough. That's just at least how many you need. If it was y is equal to x squared plus 6, the highest degree we got going there is 2, so we would want at least 3 points. You probably need more, but if you pick your points perfectly, you really only need 3. If it was y to the third is equal to x squared plus 6, my highest degree there is 3, so I would need at least 4 points to graph that. Okay? Now I'm saying at least, so you may need more, you most probably will need more. It's just that's what you need at least to graph. All right, so we want to be smart when we're choosing our x values, and this is one of the things that people always ask me every class I teach, because we don't want to just go in and go, okay, well, let's do 1, 2, 3, 4, 5. It may work for this one, but it won't work for all of them. Anybody know why? Yeah, so it's a good idea to choose from the different groups of numbers, right? And what I mean by that is you want to choose some positives, you want to choose some negatives, and a good idea is to always choose 0. So a good idea is let's do 1. Let's do, what did I choose here? Okay. Let's do that then. Let's do 1, 3, 0, -1, and -3. Let's see how that works out. We'll change it if we get a bad point. But sometimes you will. And it's a good thing to kind of see if something doesn't work out right, what do you do? Rather than just choosing these nice points I got in the example there. So to figure out the y value, this one's already solved for y. That makes it pretty easy. So if we plug in a 1, we'll have y equal to 2 times 1 plus 5, which is going to be that. That's not bad. So that means that there's a point on our graph of our equation. It's 1, 7. And let's see what else we got. We do 3. The y is equal to 2 times 3 plus 5. Which is going to be 6 plus 5, which is 11. We got another point. I graph 3, 11. Zero, always a good idea to do 0 if you can, if it's in the domain. And so y is equal to 2 times 0 plus 5. That is just going to be 5. So we have the point 0, 5. And notice I didn't use 2 for an x value. You could. I just want to space it out a little bit so you can see what kind of action's going on. This is an incredibly complex equation we're looking at right now, but they'll get more complex as we go. And let's do -1 next. So y is equal to 2 times -1 plus 5. That's going to be 3. So we have a point -1, 3. And then the last one, -3. So y equal to 2 times -3 plus 5, which is going to equal -1. So at the point -3, -1. Any questions on those? So if you wanted to pick 3, 5, 0, -3, -5, that would work. I mean, I like to have some kind of duplication on the negative and positive side. That's just my personal preference. But if you chose different values on the positive and negative, that's fine too. Oh, I'm trying to scroll there. So let's plot those points. So we have 1, 7. We're going to treat each of these as 1 tick mark. Let me make sure I got enough. 2, 3, 4, 5, 6, 7. I do not. What's the highest value? I got 11. So we may have to kind of do a little work with that. So let's say if this continues on, that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Maybe we'll have to go and find another point. Maybe we'll have to use 2 or something. So first one we got is 1, 7. So x is going to be 1, y is going to be 1, 2, 3, 4, 5, 6, 7. And so we have a point here. I'm going to label it for right now. I might have to move that, but we'll see how it goes. Questions on that? Next one I got is the 3, 11. Let's plot it for right now, and we'll see what it looks like. So we got 1, 2, 3 for x. This will be 8, 9, 10, 11. So that's going to be all the way up there. Because if you're doing this on my math lab, you wouldn't be able to put that point. They limit you to what the graph shows. So we'll figure out some way to get another point if we need it. Or I'll show you anyways. We got 0, 5. So that means it's along the y-axis because x is 0. So 1, 2, 3, 4, 5. Nope, I'm supposed to label it. And we got -1, 3. So x is -1, y is 1, 2, 3. That's right there. And then we got -3, -1. So 1, 2, 3. And then -1's down here for y. Almost messed that up. And so even if you didn't have this point up here, you can still kind of, you have a good feeling of what the graph does. Now, who knows that maybe it does that and then over here does all kind of crazy stuff, but that's all we got to work with right now. You kind of just want to make enough points so where you kind of know what the shape looks like. And we're going to learn, well, that was bad drawing. And we're going to learn some properties of functions and equations later on, especially when we get to 2, 3. But this equation does represent a line, so that's what we get. Even though mine's very curved because my hands can't draw. Any questions on that? And we're going to look at some other examples too that aren't lines. Where are those examples? Oh, there's a line right there. So this is what that graph looks like. That's taken out of the book. Let's try another one. How many do I have? 3 of these? No, I just got 2. Yeah, we'll work it out. So here I got y is equal to x squared. How many points do I need at least to graph this? I need at least 3 points. The highest degree on a variable is 2. And so we want at least 3 points. I'm planning on us having more just so you can see how many I got here. But assume you didn't know that. So what are some values y'all want to choose for x? Let's keep them kind of small so that way we don't go out of bounds. But what do y'all think?
I was always taught to go like -3 to 3. Like -3, -2, -1, 0, 1 to 3. Like I was always taught to go
Like no matter what the function was, just always -3.
either -3 or -2.
Wouldn't always work. I mean, it's a good starting spot.
That was our like starting point.
Yeah, it's a good starting spot for sure because you're seeing what's going to happen around like the origin, and then that region, that what's the word I'm looking for? Like that neighborhood of the graph. But I mean, you could have graphs where like when x is 0, y is 1,000,000, then it comes down way down the line. So in algebra, there's not a lot that we can do other than recognize what the shape of it's going to look like and plug in points. If you get to calculus, that's when you can actually determine through other methods, like, okay, this is where stuff's happening in that function and determine where to look and stuff. So there are ways to do it, but with algebra, some of it's just guesswork at that. So it is a good place to start. So, but I would always say, yeah, I mean, we definitely want to do 0. We could do a 1, 0, -1, see that where that gets us, and maybe go from there. You don't always have to do them in order. I mean, some may make it easier if you do it in order, but you don't have to do it in order. And what I mean by that is like you don't have to do 3, 2, 1, 0, -1, -2. You can do them in a different order. So that's what we're going to do here and see what happens. So if we want to figure out what the y value is for 1, that's going to be 1 squared, which is just 1, So we're gonna have a point 1, comma 1. If we do 0, 0 squared, we go to 0. And so that's 0, comma 0. That's not bad. Just want to fix my 0 up there. There we go. And if we do -1, be careful on this one if you're doing your calculator. It's going to be -1 squared. Notice I'm grouping that in a parenthesis. Otherwise, it's going to give you the wrong answer. If you're doing a calculator, that's going to be +1. So we're going to have the point -1, comma +1. Any questions on that? Yeah, we need at least 3, right? So we may need more. We'll see what we get out of this, and maybe we'll elaborate on it. And you don't have to choose 1, 0, -1. You could have chosen like 2, 0, -2. I would just say choose a positive, a 0, and a negative. Be a good start as well. So let's plot those. How does this look? All right, so every tick mark is 1, it looks like. So we got 1, comma 1. That's going to be right here. We got 0, comma 0. And we got -1, comma 1. And I was really zoomed out here. So that's what we got so far. Do we know what that's going to look like from that? You might. If you have some advanced knowledge of what that graph kind of looks like, you might know. But let's say we do some more points. We have this big graph to work with. Let's like try, like a larger number. Maybe let's try 4 and -4. And so y equal 4 squared should be 16. So we have the point 4, comma 16. And so that's going to still be on a graph. Notice the graph, the y value goes up to 20. So that will still be graphable for us. And for -4, you got y is equal to -4 squared, which is going to equal 16. So we got some. Oh, we got another term yet. I learned that a little bit. And so if we plot those, let's see, 4 is here, and 16 is here, so that's going to be my point there. 4, comma 16, and -4, comma 16. Be there. How do y'all feel about it now? Think we could draw it from that? Yeah. What if you want to do 2 more points just to make sure? What do you think you would choose? Yeah. So probably, I mean, there's 4 numbers I would think of, right? Either 2 and -2 or 3 and -3. If you do 5 or -5, it looks like it's going to go beyond our graph, right? And there's really nothing in between unless we're going to start using fractions, which let's avoid that if we can, right? So let's say we do, you want to do 3 and -3? How many numbers does it here? Oh, I just want to read this. Whatever. So y is equal to 3 squared, which should be 9. So we'll have a point 3, comma 9. And y is equal to -3 squared. Get the negative, which is also going to be 9. So -3, comma 9. And so if we plot those, 3 is, 3 is here. and 9 is here, so I have a point right there. And we'll have a similar thing on the other side, right here. And so now I got a pretty good idea of what it looks like. Let me try to draw it. But both of those attempts were really bad, so let's try it again. Something like that. Let me do it one more time. There we go. Oh. Nope. It's the there's no friction when you draw this. And so that is what our graph looks like. Anybody knows what the name of that graph is? Like that shape? Well, it's a quadratic. It's a parabola. Yeah. So we're gonna learn that more in like section 3, but chapter 3. But yeah, that's what it is. And so the 3 points you need for this, just to give you a little insight, is you need at least that bottom point there, and you need 2 points around it. Even if you have like this point, and this point, you can still get an idea of what it looks like. But you do need to have at least 3 points to do that. So if you only had this point, and this point, you'd only know that it does this. So maybe it keeps going, who knows? But they do need a specific 3 points for it to work, or just 3 points. So that is kind of the difficult process. What points do we choose? Any question on that? Do I have a graph of it? It's fine on the next page.
Is that why you always put a negative one? Like
yes, because if it's doing different activity on the other side, I guess I didn't grab that graph. And that won't always happen, right? Because you could have. That's kind of why I don't like really enjoy teaching this, because it's just like, I mean, it's kind of a little guesswork, but I mean, it could have happened over here. And so even if we had chose some negative numbers, I mean, they're just going to be way up here. So what you need to get is where that bottom of it's happening. There's a name for that, and we'll learn it later, and the size. So when we talk about quadratic functions, you'll learn how to make sure that you would graph that correctly. There is a method to do it, but at the level we're at right now, it's just kind of pick some points and go from there. So if you picked like those points and you had like a point up here, point here, a point here, and a point here, but you say, well, this is a square function, right? So it's probably going to go back up or change direction at some point. And so you have to keep going until you find where that's happening. That's what you would have to do in worst case scenario. Any other questions on that? Oh, you're on time. Cool. Okay, yeah. Today's Wednesday, right? Yeah. All right, well, let's do intercepts and then go from there, I guess. So the intercepts of a graph, that's where it touches or where it crosses the axes. So since we're doing 2 dimensions, you can have y-intercepts, you can have x-intercepts, you can have multiple of them. If it crosses on the origin, that's a bonus. It's both an x-intercept and a y-intercept, crossing both axes. So that is the different types of intercepts we can have. I always think about like an interception in football. I know not everybody's a football fan, but this is how I remember. And so it's where like the defensive player would cross the path of the ball and take it. So it's where the graph crosses the axis, crosses those paths. It's a weird way to remember stuff, but that's what I do. So maybe it'll help you. And so if we look at this crazy graph we got going on right here, you have intercepts all along this graph. They're having at -3, 3. Well, let's read out the whole coordinate system. -3, 0, 0, 3, 3/2, 0, 0, -4/3, 0, -3.5. Now we're doing decimals, and 4.5, 0. So they can happen at different numbers. You can have multiple of them. There are some restrictions we'll learn about how many intercepts you can have with a function. But with a graph or with an equation, you can have as many as you want. Equations have no rules. They're just wild, wild west. Whatever. Okay. So, oh, well, let's look at those. Let me mark all the x-intercepts. So these are all my x-intercepts. All right. We'll start shorthanding it later, but we'll do the whole word for it. Do you notice anything in common with all those? Yeah, negative 3 comma 0, 3 over 2 comma 0, 4.5 comma 0. They all have a 0, and it's a 0 for what? X value or Y value? Y value. That is true for every x-intercept that will ever be or has ever been. Yeah, I think so. Y will equal 0. Okay? Because it's going to be along that x-axis. And so for it to be along that x-axis, the y value needs to be 0. If we take a look at our y-intercepts, do you notice anything in common with those? The 0 value for x. You have 0 comma negative 3.5, 0 comma negative 3/4, and 0 comma 3. So the x value will always be 0 for the y-intercept. So the opposite variable will be 0. You start thinking about more dimensions, basically all the other variables will be 0. That's outside the scope of this class, but just in case you want to think about it. So if we want to find the intercepts for a function, y equals x squared minus 4. How do we find the x-intercepts? We'll make y what? 0. Because we know for all our intercepts, for x-intercepts, y is going to be equal to 0. So we'll just set it up that way. 0 is equal to x squared minus 4. And we can solve that equation. It's a quadratic equation, difference of 2 squares. So we can make it 0 is equal to x plus 2, x minus 2. You can also do a square root method if you feel so inclined. And so what we get from that is x is equal to plus or minus 2. So that means there's 2 x-intercepts, and those are going to be 2 comma 0, negative 2 comma 0. Any questions on that? Sometimes when they're asking you for intercepts, they'll only ask for the x value because they know what the y value is, right? So be careful in the homework. They may say answer as an ordered pair. In that case, put the whole coordinate. If they just have x is equal to, just put the value. And now if we want to do our y-intercept, what are we going to do? We're going to set x equal to 0. And so we'll have y is equal to 0 squared minus 4, which is going to give us y equals negative 4, which means that our y-intercept is going to be 0 comma negative 4. And so that is our intercepts. Notice that gave us 3 points already. We can just plot those 3 points and see what we get. So a good place to start, that we didn't know about before, but a good place to start now, is start with your intercepts. If you can find some intercepts, not every equation has them. Not every equation has intercepts. It's possible it won't. But start with that. See if you can find that. It's a good spot to start, and then work your way from there.